Okay, so hello everyone. So now I want to something important that I want to tell all of you guys, which is basically an update from what I said a few days ago. So what I said about a few days ago, if you watch, is about static pressure, pressure drop, airflow, and this static pressure versus airflow graph, and why I said that our fans are not feasible for our ventilation system design. Okay, about so today I want to elaborate more on this, and I can propose a solution. What is the best solution for our ventilation system design? Okay, all right. So what you see here, what you see here is a technical datasheet, and I've just realized that you see all the fans here, right? This is actually called series lah. They are actually the same series, which is CFM 80BG. And yeah, this is something important. I just realized it. All of these fans, all of these fans in this series, they actually have the same specification. They actually have the same specification. What I mean here is same specification. I'll try to explain more on this. All right. Okay. Um, you see these fans, right? They have different rated speed. I'll just focus here. They have the same rated speed. Not same. They have all different rated speed, different airflow, and different static pressure. Okay. And then I have came across this site. Say something like this: airflow is proportional to rotational speed. Rotational speed is what? This one lah, rated speed. Rotational speed, rated speed, same thing. In principle, airflow is proportional to rotational speed, and static pressure is proportional to the square of rotational speed. For example, doubling the rotational speed will double the airflow and quadruple the static pressure. Alright, okay, so what does it mean here? Remember the previous few days ago, I talked about this this static pressure to airflow curve is only for one specific um, fan speed, right? Fan rotational speed, right? And then if the fan rotational speed is lower, then the graph will be lower. So for example, this graph, this this static pressure to airflow curve is for a fan which has a maximum rotational speed of 8,000 rpm. And this static pressure to airflow curve is for much lower fan rotational speed lah, which is, let's say, around 2000 rpm. Okay, and then we can use this formula to make some relation. So this N2 is basically rotational speed. N1 is like rotational speed for fan 2. Yeah, for fan 2. N1 is rotational speed for fan 1. Or it can also mean rotational speed 1, rotational speed 2, and rotational speed 1. Okay, why do I say like this? Is because, like I said earlier, all these fans here, they are the same. They are the same because they belong to the same series. They belong to the same series. So I will try to prove with this using this formula. Okay, I'll try to prove using this formula. So Q is airflow, we all know this. P is static pressure. Alright, so let's try to apply this formula. Alright, okay, so let's assume this is fan 1 and this is fan 2. Okay, fan 1, fan 2. So fan 1 has rated speed of 4000 rpm. Okay, N1 is 4000 rpm, N2 is 7000 rpm. So Q1 is how much? 41.4 CFM, right? Then static pressure P1 is 0.27 inch H2O. This is not important, you can skip lah. I just want to show you guys why I say like all these fans belong to the same series. Okay, so how to find the Q2 and P2? What is the airflow and static pressure of P2? Alright, so you using the formula, Q2 equals to N2 is how much? 7000 over 4000 times Q1. Q1 is 41.4 CFM. So this is how much? .45 CFM. So this is the maximum airflow for fan 2. And how about P2? P2 is proportional to, you need to square, right? Square the rotational speed. 7000 over 4000 squared times, what's the static pressure? 0.27. And we have what? We have 0.826. Yeah, 0.827. Yeah, 827. So this is the max static pressure for fan 2. And you can see that these values are the same. 72.45 CFM is same here. 7000 RPM, 7000 RPM. 0.827 HH2O, 0.84. Okay, roughly similar. Yeah, so it's proven that you can use this formula, and these fans are basically the same. They are the same because they belong in the same series. Yes. So I hope everyone is clear on this issue now. Alright. So recently I did simulations. Okay, I did simulations comparing like all types of rotational speed, all different types of fans, from 4000 rpm to 5000 rpm to 6000 rpm to 8000 rpm. I didn't do simulation on 7000 rpm. So based on this rated speeds, I use the inlet airflow of this one lah, these values. I use inlet airflow of these values. Okay, so I'll show you. Alright, so now this scenario is for the case of 4000 rpm. Okay, 4000 rpm. So it based on the technical datasheet, the maximum airflow is 41.4 CFM and the maximum static pressure is 67 PA or 0.27 inch H2O. Same thing. Okay, and the results show that the pressure drop, if the inlet airflow is 41.4 CFM, the pressure drop is 69.2 PA and efficiency is 64.69%. Okay, and as I said earlier in the previous video, maximum static pressure must be higher than pressure drop if you want the air to pass through the heat exchanger. And you notice that 67 Pascal is below than 69.2 Pascal pressure drop. So this fan is not feasible. We cannot use this fan. So what is the next solution? How about we increase the fan speed from 4000 rpm to 5000 rpm? What is the result? Okay, now 5000 rpm. It means that the maximum airflow that it can produce is 51.74 CFM, meaning that the airflow which is entering the heat exchanger is 51.74 CFM. Okay, about the maximum static pressure is 107 Pascal. And you notice that this maximum static pressure is higher than the pressure drop. So this means that if you use 5000 RPM or 51.74 CFM, it means the fan we use is feasible. Okay. Oh, take note that I increase the fan, I increase the gap of the plates to 2 mm, which is why the pressure drop is significantly reduced from the previous design. Okay, yeah, so pressure drop is 94.9, static pressure is 107 Pascal, which is higher than the pressure drop, so this is feasible lah. And also the efficiency is 62%. Okay. Okay, how about if we use this graph? You remember the static pressure to the airflow graph, right? Okay, since like I said earlier in the previous video, static pressure is equals to pressure drop. So what I'm trying to say is, like, since the pressure drop is 94.9 Pascal, right? Remember, the pressure drop is 94.9 Pascal, right? And this is equivalent to 9.7 millimeter H2O, which is around here. Yeah, 9.7. No. Should be like very close to 10 lah, 9.7. So since the static pressure drop is 9.7 millimeter H2O, how much is this? This is probably like 5 CFM. So what it means, we have the fan rotating at 5000 RPM. So it means that, okay, sorry, this is very bad visualization. I try to make it clearer. Okay, so we have the fan blowing at 5000 RPM. Okay, and we have the heat exchanger here. So the airflow here is what? Maximum airflow, right? How much? 51.74 CFM, right? Yeah, 51.7 CFM, 51.74 CFM. And the pressure drop to the heat exchanger is how much? 94.9 Pascal, right? Yeah, 94.9 Pascal. So this means that the airflow after passing through the heat exchanger, when we use this graph, or 9.7 mm H2O. So when we use this graph, right, the airflow at the outlet of the heat exchanger is only 5 CFM. So this is the amount of air which is going to enter to the room, 5 CFM, which is definitely not enough for our ventilation. No, not enough to provide adequate ventilation. Well, our ventilation is how much? 35 CFM, right? Yeah. So which is why we need another fan to compensate this pressure drop. Okay. Now moving on. How about if we increase the fan speed even further to from 5000 RPM to 6000 RPM? Okay. And this is the max airflow from the technical datasheet, 62.09 CFM and 151 Pascal static pressure. Okay. And the pressure drop is 122 Pascal. Maximum static pressure is 151 Pascal. So pressure drop is higher. The pressure drop is so this design is also feasible. If we increase it further into 8000 RPM, which is or 82.79 CFM, the maximum static pressure is 100. Okay, this is wrong. Not 151 Pascal. it's 271 Pascal. 271 Pascal, yes. Okay. Yeah, maximum static pressure 271 Pascal, pressure drop 187 Pascal. Okay. So also the static pressure is higher than pressure drop. It means that the fan can overcome the pressure drop with the heat exchanger. How about we try to use this graph again, okay? So since, like I mentioned earlier, the pressure drop is 187 Pascal or 19 mm H2O, which is around here, right? Yeah, here, around here. Airflow is how much? 30 CFM. So if we use this kind of fan, alright, it means that this is our fan, 8000 RPM. The flow rate is how much? 82.79 CFM. Yeah, I have to make my drawing cacat a bit. Sorry. So pressure drop is how much? 187, right? 187 Pascal. And the airflow at the outlet is only 30 CFM. Almost enough, because we need 35 CFM of supply air to travel through the ventilation, to travel to the to be supplied to the room. Almost enough. Okay, almost enough. So from these results, right, we can conclude that, okay, if you notice from this graph, right, if you notice from all these results, right, the efficiency is reduced when we increase the fan speed or we increase the airflow. See, from 64.69 efficiency, 64.69% efficiency at 4000 RPM up to only 55%. 55% when we use 8000 RPM or 82.79 CFM. So conclusion is higher fan speed means lower efficiency, and also higher the fan speed, it means the design is much safer. The design is much safer. It's much safer. But also we should also take note that the higher the fan speed, higher the power consumption lah. Okay, why do I say that? And when we have higher fan speed, it means it's safer. Because when we look at 51 point, okay, when we look at this fan, right, 51.74 CFM, right, you see that the static pressure is 107 Pascal and the pressure drop is 94.9. Like the gap, the difference of this pressure is like very small, you know. And we all know that the actual pressure drop in our actual heat exchanger will be much higher than 94.9 Pascal, you know. Maybe the actual pressure drop will be like 105 Pascal, you know. Yeah, we basically, like, the gap is very small. And if we increase the fan speed, okay, for this case, 6000 RPM, static pressure is 151 Pascal and pressure drop is 122 Pascal. You can see that the gap is much higher. You can see that the gap is the difference between this pressure is much higher than the 5000 RPM one. We move further to 82.79 CFM. Static pressure is 271 Pascal. Pressure drop is only 187 Pascal. So the difference between these pressures, right? The difference between these pressures is almost 100 Pascal. So yeah, that's why I said that the higher the fan speed, the safer the design. Okay, so what is my proposed solution? My proposed solution is we use this one, 5000 rpm. We use the 5000 rpm fan because, like I said, it is like the pressure drop is still, the static pressure is still above than the pressure drop, and it has the highest efficiency, which is 62.3%. Okay, and also the power consumption is much lower if you use if you use um if you use lower fan speed lah. Okay, so yeah, like I said earlier, I propose that this fan is our solution. Okay, our solution, which is this fan, yes, this fan. This is our solution. So yeah, as you can see, right, what's our input? Yeah, our input, the power consumption. The power consumption is only 4.2 watts compared to 13.2 watt for if you use a much higher fan speed, you know. This is also one important thing to consider about power consumption. Alright. Okay, so how do we overcome this issue? Yeah, like I said earlier, because of the pressure drop, the ventilation rate will be much reduced, right? Like the ventilation rate at the outlet is only 5 cfm. We need 35 cfm. So my proposed solution is we have to use a fan lah. Another fan here. We have to use another fan here. But just use a much cheaper alternative fan. Okay. We use a much cheaper fan at this outlet. Okay, what I meant, right? Here is our ventilation system. Okay, so this is outdoor air, this is supply air, this is return air. Okay, this is exhaust air. You notice that I do not include a fan here. Yes, you notice that I do not include a fan here. I hope like 3 fans work, because what we care is supply air, right? We don't care about exhaust air, we only care about supply air. So this is why I just suggest 3 fans. So the fan here, this fan here is the fans like I told you lah. We all know what fan we are using here, right? This is the 51.74 cfm, and what is the static pressure, 107 pascal fan, right? Yeah. Okay, how about this fan here? This fan here is placed at the outlet, right? So we don't really need I think we don't really have to care about static pressure for this fan. No need to care about static pressure for this fan. So for this fan, I suggest that we just need a fan that can provide enough ventilation rate, which is 35 cfm. Yeah. So what I want to say is that we have this fan, right? Yeah, we have this fan, right? So I suggest that we use this fan at the outlet. We use this fan at the outlet because it's cheap, 27.4 ringgit. Okay, 27.4 ringgit. So our total cost of the fan is, this is RM 27 ringgit, right? This is 27 ringgit. And then the cost of one of this fan is around 69 ringgit. 69 ringgit. So the total cost of these 3 fans will be by the way, by the way, our budget of the fans, right? Our budget for the fans is this is the initial budget I set for the fans. $176. Tapi if possible, 160. We try to achieve RM160 for budget for fans. And so since we have these 3 fans, right, our budget by right should be just enough for our ventilation system. Okay, yeah, so this is my solution lah. My solution, this one. I hope this will be feasible. And also I wanted to tell you guys something. Oh, if you guys want to see the simulation result, I can show you here. You can see my screen. Okay, yeah, you can look at this file lah. I already share this file. Yeah, this file. This is where I have all the results. You can see, you can look at the flow simulation here. 82.79, 41 CFM, 51.74 CFM, 62.09 CFM. Okay, I've already mentioned them all here. Also, yeah, I tried to make some modifications on our heat exchanger, which is this one. If you look at this file, so what I did is I increased the I increased the length of the plate. Okay, so this is the original, this is the new one. I increased the length of the plate from 250 to 325 and reduced the width from 188.2 to 160. So the reason why I reduced the width is because our fan dimension our fan dimension is only 80 times 80. So if you use a 188.2 width, it means that the width is already like way too much. I felt like the width is way too much for our fans. So I guess it's better that we reduce the width while also increasing the plate length, increasing the length. And also I reduced the number of plates. I reduced the number of plates from 46 plates to 44 plates. And the results I get is even worse. Yeah, this is the results for 51.74 CFM. And as you notice that initially our pressure drop is only 94 Pascal, right, and our efficiency is 62%, right. This is our original. Yeah, so what I can conclude is that if we modify the plate design by increasing the length or reducing the width, the results are much worse. So we just stick to the original design, because you can see lah, not only the pressure drop is much higher, the efficiency is also lower. So yeah, let's just stick to this original design we have. Okay, so like I said, this is our solution. This is the fans that we can use. Hopefully it's going to work. We use this kind of fan. Already explained why. So I think that's all from my video. Thank you for watching.